Hello everyone, our project is Battle Tetris, Power Up Bubble Edition, a single-player, competitive Tetris game featuring physics skill balls and a smart CPU. Players select a difficulty from the main menu, which adjusts both the CPU's intelligence and the block's initial falling speed. While web parameter passing and screen control are traditionally handled by JavaScript, our project's standout feature is completely outscoring the game's core brain to Python. We build a web's button layer infrastructure in 3 key steps. First, PyScript configuration. We use a fetch tag in the HTML header to directly load our pure Python toolkit into the browser's virtual environment, achieving a clean modular design. Second, URL parameter parsing. When transitioning pages with difficulty data, Python intercepts it. Using string splitting and a simple loop, we automatically convert the URL parameters into Python's preferred dictionary format. Third, difficulty initialization. The program extracts the difficulty value from the dictionary, calls getDifficultyInterval to find the corresponding millisecond delay, and assigning it to base drop interval to directly set the base falling speed.
Next, I will take you deep into the most classic and core operational mechanics of this game. What you are seeing on the screen now is actually gameplay footage. In a standard Tetris game, the core loop basically contains of 4 actions: block generation, movement, and rotation, blocking at the bottom. And finally, line cleaning for points. In our project, this classic law of the block world does not rely on JavaScript for logic at all. Instead, it is 100% computed directly in the browser by underlying Python code. Now, let me break down the intuitive yet ingenious algorithm design behind this. First, the digitalization of the game board. We designed the Tetris state class and utilized Python's concise list comprehension to create a 2D list, self.board, with a width of 10 and a height of 20 to represent the game board. The number 0 represents an empty space, while the rest are filled with color codes for the blocks. This is the sole foundation for all subsequent collision calculations. Next is ensuring fair 7-bag random generation. To solve the pain point of not getting the long I block for consecutive turns, we implemented the international standard algorithm. We put the 7 basic shapes into a bag, which is a list, use the built-in random function shuffle to mix them, and pop one out from the bag every time a new block is generated. When the bag is empty, we reload it. This balances both randomness and fairness. Finally, the block locking and line cleaning mechanics. When a block touches the bottom and locks, the program scans every row of the 2D array. If a row has no zeros, meaning the whole row is filled, we increment the cleared line count and insert a completely empty row at the very top, perfectly achieving the effect of line cleaning and block dropping.
Next, I want to introduce the 2 core features that makes this game unique: dynamic power-up bubbles and the automated AI opponent. As you can see on the screen, there are several circular bubbles with special icons floating and bouncing around the board. When the player's block drops and crushes these bubbles, special abilities are triggered. For example, you might get a gravity field to eliminate gaps, or inflict a blind stat on the opponent to obscure their screen. On the other side, the CPU opponent can accurately and rapidly find the optimal drop locations for continuous line players. This is also accomplished through high-speed Python computations in the background. The microphysics engine for the bubbles update. We wrote a dedicated update function for the bubbles, introducing the concept of delta time in every video frame. Python updates its absolute coordinates based on the bubble's velocity. When the coordinates exceed the width or height of the bird, we directly multiply the velocity by -1, achieving a perfect bouncing effect. The skill dispatch mechanism. When the block overlaps with a bubble, the program triggers the dispatch center. Based on the skill type, it decides whether to modify the board state of oneself or the opponent. This object-oriented design makes future feature expansions incredibly easy. The AI opponent greedy algorithm. When a new block appears, the AI instantly uses a double loop to brute force and simulate all possible rotation angles and all possible x-axis drop points for that block. Then it evaluates the results. If the drop location creates more holes or makes the overall height too much or too high, a massive penalty is applied to the score. Ultimately, the AI chooses the position with the lowest penalty to execute the drop.
Using Python alone for front-end rendering causes terrible performance, so we adopted an outsourcing strategy, which is Python handles the logic and JavaScript handles all the rendering. Here's how we connected them. The first is Python calls JS. After Python calculates the board state, it serializes the data into JSON using JSON dumps, then calls the JavaScript function JS drawboard via PyScript's window object to handle all rendering. The second is JS called Python. We set up a keyboard event listener in JavaScript. When the player presses an arrow key, JS calls window PyAction to trigger Python's movement logic directly. The third is cross-language binding with create proxy. Since Python and JavaScript run in separate memory environments, we use Pyodide's create proxy to wrap Python functions as proxies on the window object. It is what keeps the game running smoothly at 60 FPS. In short, JSON serialization and create proxy gave us a clean architecture, which is Python for logic and JavaScript for rendering. This is our Battle Tetris presentation. Thank you.